Thank you so much for the introduction. Good afternoon, everyone. My name is Junyi Zhao. Today, I'm going to present my internship project at Meta Reality Labs. So the work titled TouchpadAnyWear, you can pay attention that it's wearables wear, not everywhere's wear. So the motivation. So in this work, we aim to address three key challenges for human-computer interaction, especially gesture inputs. Number one, the gesture inputs with high degree freedoms. So in the field, tapping, pinching large swaps are broadly achieved, but it's probably inefficient for more complex interactions. So if we can achieve the continuous small snaps in the 2D plane, we can potentially replicate the functionality of a touchpad, the touchpad on your laptop, but right now it can on your finger. So we aim to develop the high spatial resolution tactile sensors. The second challenge, motion artifacts. So finger is one of the most flexible part on the human bodies, especially for tactile input. You can imagine that you do the input, but at the same time, you can naturally bend your finger. So which can confuse the system. This is a real input or just a motion artifacts. So we aim for develop a robust tactile sensor that are insensitive to motion artifacts. Our strategies include poly-islands design and the kirigami design. And thirdly, how to make it wearable. So we're gonna show how to seamlessly integrate the sensors with Textile. Then let's take a look at the state of our technologies for sum to index gesture input. For example, IMU, photoreflective sensors, magnetic sensors, or depth camera plus algorithms. They're all effective. They all have their own strengths. So for the conventional mechanical sensors like capacitor sensor or resistor sensors, they still offer their distinct advantages in certain aspects. For example, reduced bulk, low power consumptions, resilience against environmental interferences, and the integrations on various substrates, especially for wearable applications on soft materials. Then how to combine the sensor with textiles. Typically in the field, the most common use way is to develop a sensor patch, then attach it on the textile by lamination, sewing, or stitching or embroidering. So here we want to clearly define two concepts. The first one, textile-based sensor. It means that the textile is utilized as a substrate or backing support. The other concept is textile-integrated sensor. It means that textile is an integral component which is functional within the sensor. So to demonstrate the capability of our sensor, we did some interaction explorations. The first one is a 1D or 2D continuous input. As you can see, we can not only do swaps, we can do micro gestures. Means that very minimum input. So typically this is a swap, but this is a micro gesture, like just you intend to move, but actually didn't move. Because this is high spatial resolution, so we can detect it. And of course, we can replicate a joystick on the finger. This is a demonstration of the 2D navigation by micro gestures. It's just like a touchpad. You can control up, down, left, right. You can click it for the confirmations. And of course, this is a force sensor, so it can detect the levels of the input force. You can press it harder, you can tell you really push harder, and you can't just squeeze the ball. You can push very hard, you can squeeze it, you can explode it. And we also demonstrate a wearable form factor. This is a finger sleeve. You just wear it, you can do the 1D continuous input, you can do swaps, you can also do this micro swaps for the privacy purposes. And of course, this you can give different force, different levels. So here I'm gonna talk about the sensor feature highlights. This is a detailed structure of the high density textile integrated motion artifact capacitor sensor arrays. And to enable the accessibility, most of the materials are commercially available or off the shelf. And the working principles. So first, I would like to talk about the requirements for selecting dielectric materials for capacitor sensors. It should be compressible along the z-axis or the thickness directions, and this deformation should be recoverable. And of course, the material itself should be insulated. That's why people always select like silicone or polymer materials. So how about fabrics, especially the knitted fabric? Take a look at this cross-sectional wheel of the knitted fabric. This unique structure allows the fabric being pressed and recovered. So it appears to match all the requirements at least here. So how about using the knitted fabric as a dielectric layer? Then what is the uniqueness of our capacitor sensor? Number one, the poly islands is designed for high sensitivity. So we create the dorm-shaped polymer dots on top of the fabrics, referred as poly islands. And you can see this sensor schematic. If I press it, the polymer and the textile composite can deform. And this deformation induces the capacitor change, so we can read the change. Then we try to find the optimal fabrics for this idea. So we investigated different knitted fabric, but all commercially available. You can see they either have different thickness or just by different materials. And we categorize the force over the capacitive distance. So you can see that the blue curve, which is say the fabric 3, provided the maximum compressibility, means that the maximum sensitivity. Then by creating these polymer dots on the fabric 3, we can further boost the sensitivity of the sensor by increasing the compressibility. And then the poly islands has another functionality or purposes for string locking. So again, as I mentioned, I want to deal with the motion artifact issues. And there's a common sense that at a given stress, by increasing material modulus, we can decrease the strain. That's why a common strategy is we do a coating, evenly coating, for example, a high stiffness silicone material on the fabrics as a composite. When you stretch it, the overall modulus increase, so we can lower the strain. But in this project, we propose a new strategy, methodology called isolated coating. So we can locally deposit the silicone material to customize the local stiffness of the textile. Then we can design the strain distributions. For example, here's a sample with an isolated coated polymer dot. When we stretch 20%, this dot can actually just be stretched 2%. You can calculate the elongations. Upon 40% stretching, only 5% elongation were observed. So it changed. We can customize the distributions of the strain. And here is, I assume everyone had this experience that if you wear a bandage, it's very hard to bend because the stiffness mismatch between the bandage and your skin. This is also a common issue for sensors, especially finger interactive sensors. This is a planar device. If you try to bend the finger, you can see there are lots of random creases. And highly likely it going through your pixels, means that the creases is pressing your pixel. That's why you even didn't touch the sample, but you actually see the signal change. So how to solve it? We use the laser engraving some sleeves, and we can design the orientations and the creases, especially the distribution of the creases. And you can see that it can just avoid the pixels. Again, this time we bend it. You can see the creases never going through your pixels, never pressing your pixels. Then it can dramatically eliminate the motion artifact. At the same time, the device is more bendable, it's more comfortable for wearing. So this is an overview of the fabrication pipeline. We call it direct on textile fabrication because we can directly pattern the dots on the textile surface. We didn't do any molding, we didn't do any transfer, no laminations for this step. And for the electrodes, we just pattern the stretchable silver paste on the TPU film and do the laser engravings for the kirigami design. Eventually, we just laminate the components. And this fabrication flow is highly scalable, customizable. We demonstrate 2 prototypes. The first one is a very regular square-shaped touchpad. It has a total of 8 by 8, 64 pixels in a gray shape. The second one is a T-shaped finger sleeve. It's designed for more comfortable finger wearing, especially during the bending. And in order to demonstrate the effectiveness of our devices, we did 3 simple user studies. So this is an overview of the system. The signal readout from the capacitor sensor really going through our sensing electronics to the microcontrollers, and then do the signal processing, gesture recognition, the user interfaces on the PC side. So the uniqueness or the advantage of our system is we can provide rich tactile information, including the touch, location, size, and the force. The study number 1, this is a simple micro gesture recognition test. 5 gestures, right, up, down, and the tap. And the mean accuracy across all the gestures is over 93%. And the median compute time is 1.05 seconds. And then we involve more complex stroke-based gestures. So this time, you can see some check mark, heart, question mark, smile, or even kind of complex VAPS gestures. And the overall accuracy is above 91%. And more interestingly, owing to the high spatial resolution of the device, we can actually track each individual's drawing, which is very meaningful for advanced learning or training purposes. And number 3, we tested the 2D continuous input. This is really replicating the functionality of a touchpad. So we employed the Fitz's law putting tasks in both 1D and the 2D scenarios, and both achieve approximately 1 beat per second result. And the limitation feature works. So in this work, we're trying to make everything accessible. We just apply this automatic dispensing system. It's a direct ink writing machine, which is good for prototyping and customizations. However, it's probably not suitable or compatible for large-scale manufacturing. So to enhance the yield and the quality control, we can consider to use micromolding for poly islands creation and also screen printings for large-scale electrodes printing. And of course, we can make it untethered, variable, wireless communications for more practical variable application. And of course, we can apply it for the machine side to build the human-machine interactive interfaces. So to summarize, in this work, we address 3 key challenges in the textile sensors: high spatial resolution, and motion artifact tolerance, and the seamless integration with the textiles. And we propose this poly islands concept, which can increase the sensor's sensitivity. At the same time, we can program the textiles' local stiffness for string locking purposes, again, to solve the motion artifact issues. Of course, we demonstrate different form factors for a touchpad and for a variable finger sleeve. And lastly, thanks Meta Reality Labs and my mentors supporting my research. And thank you all for attending, and welcome any questions. Thank you.
Hello, it's like a really nice presentation, and very luckily, I work with one of the previous work you mentioned in the slides, which is also like embedded a sensor within the textile structure. But when we are working in that project, we found it's very difficult to connect the high resolution electrode into the sensor. How do you develop the strong both electrical and a mechanical connection between those flexible PCB and the textile?
Okay. So I assume your question is about how to connect the device to the FPCB.
Yeah.
Yeah. So in the lab, typical ways is just use a silver paste, but it's not high resolution. It's ugly. So in this work, we use an anisotropic conductive tape, which is a kind of industrial preferred way. And this tape, if you don't know, it's only conductive along the Z-axis.
Right,
yeah, this is commonly used for the display industry.
Yeah, but in our case, when we are doing our experiment, it's still likely to have some short circuits. I don't know whether it's the same for your.
Then you have to optimize it. I made it.
All right, great.
Yeah. Thank you.
Hi, great project.
Thank you.
Cedric Honnête from MIT. I was curious if you looked into the limits of the density that you can get. So for example, some phones used to have, or still have, fingerprint sensors behind, and apparently it's capacitive. I wonder how far we could go with this process.
Yeah, this is a very, very good question. So I do trying to investigate what is the limitation. So by now, what I can achieve is 49 pixels per centimeter square, means that is a 7 by 7 array within 1 centimeter square. But the limitation, I think, is not the method, it's the machine. Because I use a commercial dispensing tool, you can purchase the printing tip, but it's limited the size. So that is one limited. The second one, because this one is built on the fabrics, you know, the knitted fabric, you use a thread. The thread diameter is roughly a few hundred microns, so you cannot go beyond that. Otherwise, it cannot stand there. It just go inside the fabrics. But of course, if you want to select more rigid substrate, like a polyimide, some polymers, for sure, you can make it more high resolutions. Yeah.
Thank you.
Thank you.